Welcome back. We're going to continue with Chapter 11, Momentum and Impulse. Remember, momentum is conserved whenever the external forces add up to zero. If the net external force on a system is equal to zero, then the momentum of that system is equal to zero. If not, then the momentum is not conserved. Internal forces are irrelevant for the conservation of momentum. In fact, they all cancel and by Newton's third law, and that's why momentum is conserved. Now, remember, when you have now the mechanical energy, when is it conserved? It's only conserved if the net, or if there are no non-conservative forces involved. Non-conservative forces usually mean frictional forces and like air resistance and so on. We started talking about inelastic collisions, collisions where two objects stick together. In such a collision, momentum is conserved because, sure, it's inelastic, there are frictional forces, there is bending, and so on. However, those forces are internal to that system. Mechanical energy, on the other hand, because of the existence of those non-conservative forces when two objects stick together, mechanical energy is not conserved during right before and right after the collision. So we will look at this example here. It's called the ballistic pendulum because, and it's found in every textbook, and the reason for this problem being found in every textbook is because it combines or tests your understanding of conservation of momentum and conservation of energy and when to apply each of them. Okay? So here's the example. You have a 10-gram bullet is fired into a 1,200-gram wood block hanging from a 150 centimeter long string. The bullet embeds itself into the block and the block swings out to an angle of 40 degrees. And the question is, what was the speed of the bullet? So the bullet was fired. What was the speed of that bullet? So let me show you the context of this problem and then sketch an example of it. Sketch a diagram to illustrate what's going on. So let me go to the board. So here is the situation. Imagine you're in the maybe 1800s. You have a rifle and it fires a bullet and you would like to know what the speed of that bullet is. You don't have very quick stopwatches, or you don't have cameras at the time, and so you cannot measure the speed of the bullet directly. However, people came with this clever way of measuring the speed of the bullet, and here is how it goes. You have the bullet here. Here it is. Let me draw the block first. Here's a block, and the block will have a mass here. Let me call it, since it's a wooden block, I will call it MW, the mass of the wood. It happens to be 1,200 grams, but let's work with symbols for now. All right? And the bullet is fired like this. Here is the bullet. And it has a certain speed, V initial. And this is M bullet. Let me call it just here. And V for bullet. Fire the bullet horizontally. The bullet collides with the block. So this is step one, right before collision. Let me draw the bullet. Imagine the bullet is like really close. It's about to collide with the block. The block is hanging. The block has an initial speed 0. So the next step is that the bullet goes into the block really quick, right? So that it's still at the same level here, and embeds itself into the block. So you have the total mass now is the mass of the wood plus the mass of the bullet, and they will be moving at some common speed after the collision. Let me call it V. This is V initial, and the speed now after the collision, I would call it V. Okay, so the collision has happened. What happens next? What happens next is, so let's call this one here step 1, step 2, bullet and the block, they will swing. So here is the initial level, so they will swing. They will go like this and rise a little bit. The mass of the bullet plus the mass of the block, they will rise. And they rose here because this angle here is 40 degrees. It swings by 40-degree angle. Okay, and we will talk about each of them. So this is finally step 3. And when it comes to the highest point, the speed here, v is equal to 0. The speed here, v final, let's call it v final, is equal to 0 because it will swing and it goes higher and higher until it can't go anymore. And it is at a height here. Let's call it height h. We will figure what h is in a moment. Okay? I hope you see what's going on. Right before collision, right after the collision, collision has happened now and it's swinging. Like that. And we're going to analyze this at each step. So in going from step 1 to 2, in going from 1 to 2, let me ask you, what's the net force on the bullet? Well, the net force on the bullet will be just the gravitational force. On the wood, you got the tension, it's acting upward, and mg acting downward, gravitational force, but they cancel. It's just the thrust, so it's equal to 0. They collide. They collide. Right before collision, right after collision, I'm asking, is the momentum conserved in the x direction? Because in order to figure out the speed, we have to use either maybe conservation of momentum or conservation of energy. So, is momentum conserved right before collision, right after collision? And the answer is the momentum is conserved in the x direction. The reason is because there is no net external force in the x direction. Yes, the block hits the bullet, applies a force on the, the bullet hits the block, applies a force on the block, but the block applies just as much force on the bullet, and that's an internal force, and it cancels. And so we're asking for this bullet plus block system, what is the net external force in the x direction? And the answer is there is none. It's 0. So momentum is conserved. Energy, however, right before collision, right after collision, the energy is not, because when the bullet hits the block, there's definitely a non-conservative force because the bullet has to basically drill a hole and get into the block. There is frictional force between them, and so you cannot use conservation of energy there, conservation of mechanical energy. So we're going to use conservation of momentum in going step 1 to step 2, and then we will worry about what happens between step 2 and step 3. So we'll use conservation of momentum. So the momentum at step 1 will equal to the momentum at step 2. Momentum right before collision equals to the momentum right after the collision. The momentum right before collision would be the momentum of the bullet plus the momentum of the wooden block. The momentum of the wooden block is equal to 0. However, the momentum of the bullet is just, by definition, it's mass times velocity, and the velocity is in the x direction. So mass of the bullet times the speed of the bullet. So the mass of the bullet times the speed of the bullet before collision, that's the total momentum before collision. The block didn't have any momentum. Right after collision, they stick together and move at one common velocity called v. So the momentum after collision will be the mass, their total mass after collision. That's the bullet plus the mass of the wooden block and times their speed after collision. And therefore, their speed after collision will be, we just divide by this, we solve for it, we get, it will be the mass of the bullet times the speed of the bullet at the beginning divided by the mass of the bullet plus the mass of the wood. That's the speed after collision. By the way, I didn't finish the story. Why would you use this? Why did they come up with this system? The speed of the bullet is very high. It's several hundred meters per second, so it's hard to measure. However, when it hits the block, then they move slow enough, and you don't even have to measure the speed when it's slow enough. You just measure, you see how high they got, and then you can work backward to figure out the speed, and that's exactly what we're going to do. So this is really easy. You can imagine you have a big chunk of wood in your 1800s bench, fire a bullet into it, swings, and then you can easily measure that. You could see it with the naked eye, how high it went, and you can easily measure it. All right, so that's V after collision. So now we go to step 2 to 3. And going from here to here, I ask, is the net external force equal to 0? And the answer is no. The net external force in the x direction is not equal to 0, and also in the y direction it's not equal to 0. Why? Well, the block is rising. It means the tension is higher. During the rise, the tension has a larger value than mg, and also the tension points in this direction, and so it has a component in the x direction. So the net external force on the bullet and the block is not equal to 0. And by the way, B and B, no, it should be B and W. Okay. So there is a net external force during the rise here when it's swinging, so you cannot use conservation of momentum. Okay. See, we used conservation of momentum in this brief moment, right before collision, right after collision. Take it as like a millisecond or something, like a really short period of time, we were able to use conservation of momentum. Now, when it's swinging up, you cannot use conservation of momentum. You will use conservation of energy. You might say, I just told you, the mechanical energy was not conserved, so how can we use it in this step? Yes. Going from here to here, you lost some of the mechanical energy during the collision due to the frictional forces. In fact, the block will get very hot, and it might even light up, might catch fire. So we cannot use conservation energy here. However, once the collision has happened, the energy that you have, if there are no more collisions afterwards, it's going to be conserved. So let's say after collision, during the collision you lost 5 joules and you have 50 joules remaining. Let's say you have 50 joules remaining. You started with 55 joules before collision. You ended with just 50 joules after collision, so you lost 5 joules. Now those 50 joules that you have remained will now be conserved, and the wood and the bullet will just keep swinging back and forth. That energy is now conserved because there are no more non-conservative forces acting. And therefore, we're going to use conservation of energy in going from this step to this step. So that's important, and that's why this problem is found in all textbooks. So in going from here to here, we're going to use conservation of energy. At this moment here, the energy is all kinetic. When it rises and it stops, the kinetic energy is 0, and the energy is all potential. So we're going to just say the kinetic energy here will equal to the potential energy there. So that's C. So we'll use conservation of energy. Kinetic energy here is 1/2 mv squared for kinetic. So it will be 1/2 mv squared. The mass is the mass of the bullet plus the mass of the wood times v squared. I'll put just v squared. The speed after the collision squared. Plus, actually not plus, equals to, now it rises and it goes high. So it will be the mass times gravity times height, because that's the potential energy. The mass, which is the mass of the bullet, plus the mass of the wood, times gravity, times the height. We will figure what the height is in a moment. And, well, here is something, at least something nice happens. Okay, something nice happens. Those cancel. So I have 1/2 v squared. But what is v? Because I want to work backward and talk about v initial of the bullet, so I will substitute. Instead of v, I will put mass bullet, v bullet initial, mb, mw. So I have mass of the bullet, v initial of the bullet, divided by the mass of the bullet, plus the mass of the wood, equals to g times h. Now what is the height? What's the height? Well, think about it. Let me just try to draw it here. Let's say this is the length L. And when they were here, this is still the length L. This is L. When it swings, you have this height h. So from here to here, it's L. This is theta, 40 degrees. So this is the adjacent. So this is L times the cosine of theta. That's L cosine of theta. So H will be this whole thing, which is L, minus L cosine theta. So it will be L minus L times the cosine of theta. Which L is the length of this pendulum here. And L is given to us. It's 1.5 meters, 150 centimeters. So that's 1.5 meters. And theta is 40 degrees. So G times H, and H is L minus L cosine theta. Let me factor the L, so it will be L times 1 minus the cosine of theta, like so. That's H, right? I just factored the L. Okay, so I have this. Let me multiply both sides by 2, and then take the square root, and then solve for V initial. So let's multiply by 2 and take the square root first. So when you multiply by 2, you will have, on the right-hand side, you will have 2G L 1 minus the cosine of theta. And on the right, on the left side, you have M B V initial over M B plus M W. And it's squared, but let's take the square root of both sides. So we have this. Now we will multiply MB plus MW and then divide by this to solve for V initial. So we get V initial will be M block plus M bullet plus M wood divided by M bullet times the square root of 2G L 1 minus the cosine of theta. Like so. And now you plug in the numbers. The mass of the bullet is 10 grams. Divide by 1,000 to make it kilograms. So that's 0.01. The block, 1,200 grams. That's 1.2 kilograms. So don't make mistakes in the unit conversion. The initial. Well, actually, that's it. I'm not going to, I will just give you the answer. I will just write it down. You should double check it on your own. According to the answer, it's about 320 meters per second. But let me just quickly do it to make sure that everything's correct. So the bullet is 0.01 kilograms. We have to divide 10 by 1,000, so 0.01. Plus the mass of the block is 1.2. And then divide by the mass of the bullet, which is 0.01. Times. And now we do the square root. So 2 times 9.8 times L. What's L? L is 1.5 meters, right? Because 1.5, and then times 1 minus the cosine of 40 degrees, and then take the square root of that. I get about 317 meters per second. About 320, as the book says. Okay. So that's so much for that one. I would like to now go to elastic collisions. And in particular, we're going to talk about perfectly elastic collisions. So a perfectly elastic collision is a collision in which both the mechanical energy and the momentum are conserved. And we're going to take this example. You have like a pool or a billiard ball, like really hard, rigid sphere. It comes in with an initial velocity. You have another ball here. It's just sitting there. So V1 initial is some speed. Let's say it's known to us. Let's say it's 10 meters per second. We know the masses. So given them M1, given M2, and given V1 initial, and V2 initial is equal to 0, what would the final speed of M1 and what would the final speed of M2 be? What would they be? What is V1 final and V2 final? So we have two unknowns. So if you use just conservation of momentum in one dimension, that gives you one equation. You need a second one. Well, fortunately, if they don't stick together and it's perfectly elastic, the mechanical energy is conserved. So we get a second equation using the kinetic energy. When I say mechanical energy, it's really kinetic because you're not changing height. And so the potential energy is just whatever it was before, it's equal to whatever it was later. So those cancel. So it's just, when I say mechanical, it's really kinetic. So this is after. So let's write down the momentum before collision. Momentum before collision, P initial, will be m1 v1 initial, m1 v1 initial, plus m2 v2 initial, but that's 0. And the momentum after collision will be like this. I have m1 v1 final plus m2 v2 final. Notice when m1 hits m2, m2 can experience the force from the left, so it has to experience the force from the left or to the right. It will only go to the right. But m1, three things can happen. It can hit v2 and then continue moving to the right. It can hit v2 and come to a stop, or it can hit m2 and come to a stop, or it can hit m2 and then bounce back. If m2 is super heavy, imagine like you take a ping pong ball and hit a bowling ball. The ping pong ball will bounce back if it's so light compared to this one. And so three things could happen. So v1 could be plus, minus, or 0. So we're just going to write it like that and then let the math tell us, math and physics. So this is the momentum after the collision. And now the total mechanical energy before collision. So we take the potential energy here, 0. So the mechanical energy before and after is just the kinetic energy. So the kinetic energy before collision is 1/2 m1 v1 initial squared. That's it. This one doesn't have any speed, so 0. And the kinetic energy after the collision, both of them could possibly be moving, so it would be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And just a warning, there is a little bit of algebra here. Not too much, but there is some algebra. So I'm going to use conservation of momentum. And by when we use conservation of momentum, we'll have this is equal to that. So we'll have P initial equals to P final, and therefore M1 V1 initial is equal to M1 V1 final plus M2 V2 final. And for reasons that will become clear, let me take this one to the other side and factor M1. So I'll have M1 times V1 initial minus V1 final is equal to M2 V2 final. Right, I just took this one here and factored the M1. And then I'm going to divide both sides by M1. And when I do that, I will get V1 initial minus V1 final is equal to M2 over M1 V2 final. Right? Make sure it's, yes, so you can see it. Good. We now go to the conservation of kinetic energy. So I have this equation here. Let me call it number 1. Let's use conservation of kinetic energy now, because it's elastic. So K1 equals to K kinetic energy initially, Ki equals to K final, Kf. And let's set them equal. 1/2 M1 V1 initial squared. We get 1/2 M1 V1 initial squared equals to the kinetic energy at the end, which is 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. I'm going to take this to the other side. First of all, multiply everything by 2, so we get rid of this 1/2. Take this to the other side and factor the M1, so we get M1 V1 initial squared minus V1 final squared is equal to M2 V2 final squared, like so. And this is a difference between two squares, like if you have A squared minus B squared is equal to what? Would be A minus B times A plus B. That's the trick I'm going to use. So this will be M1 V1 initial minus V1 final times what? Yeah, V1 initial plus V1 final equals to M2 V2 final squared. V2 final squared. Okay. And now one thing is going to cancel. I'm going to, look here, M1 V1 initial minus V1 final. This one. M1 V1 initial minus V1 final. I'm going to replace it because M1 V1 initial minus V1 final is equal to M2 V2 final. I'm going to replace it by M2 V2 final. M2 V2 final, okay, times V1 initial plus V1 final equals 2. Here, this is M2 V2 final squared. I'm going to write it as M2 V2 final. Instead of V2 final squared, I'm going to write V2 times V2 final. V2 final times V2 final. And the reason for that is M2 V2 final, M2 V2 final on both sides cancel. And so look at this. We have the following equation now. We get V1 initial plus V1 final is equal to V2 final. Look at that. And so it became like a really simple equation. And let me put this one right under it. V1 initial minus V1 final equals to M2 over M1 V2 final. So V1 initial minus V1 final equals to M2 over M1 V2 final. So I have these two equations. I'm going to add them together. When you add them, this cancels. And you have twice V1 initial equals to, when you add these and factor the V2 final, you get V2 final. And here you have parentheses. You will have 1 plus M2 over M1. And now make a common denominator and solve for V2 final. Let me make a common denominator first. So you will have M2. Oh, this is M1. It will be M1 plus M2 over M1 V2 final equals to 2 V1 initial, and therefore V2 final will be, well, multiply by M1 and divide by M1 plus M2 will be 2 M1 over M1 plus M2 V1 initial. All right. Finally, what this says, if you know the two masses and V1 initial, you can find what V2 is. So let's say this is 1 kilogram and this is, so 1 kilogram, and let's say this one is 3 kilograms and this one is 5 meters per second. Well, then you can get V2 final. But what's V1 final? V1 final, well, V1 final would be V2 final minus V1 initial. You could just use this and plug in for V2 final, plug in this whole thing. That will give you V1 final equals, I'm going to just write it down from here. It will be, I'll just write it down. It will be M1 minus M2 divided by M1 plus M2. It will be M1 minus M2 divided by M1 plus M2 V1 initial. So, and I'm going to make a box around this one. Let me make sure I'm okay with time. Yeah, I have like 1 or 2 minutes. Notice, if the two masses are equal, then M1 minus M2 is 0. That tells you V1 final will come to a stop. And you probably experienced that when you play pool. When you hit one ball and it hits the second one, the ball that hit will come to rest and the other one carries on with the same speed. Because if m1 is equal to m2, you will have twice m1 here because they're equal, and you just have v2 final will equal to v1 initial. On the other hand, if m1 is heavier than m2, then v1 final will be positive because larger minus smaller will be positive. So if you have like a billiard or a bowling ball and it hits a ping pong ball, the bowling ball will hit the ping pong ball, but the ping pong will keep going will go that way, but the bowling ball will just also keep going. It doesn't bounce back. On the other hand, if m1 is less than m2, then this is a negative quantity, and it says v1 will be backward, which is like if you hit a ping pong ball on a billiard on a bowling ball, the bowling ball will go a little bit to the right at a certain speed, but the ping pong will bounce back. And that's it. Next, we'll talk about rifles and when this is collisions. How about when they move apart, explosions? So let's talk about that in a moment.